Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 13 on higher derivatives.
In single variable calculus, the derivative of a function is another function of the same type. Therefore, one can iterate the construction, computing rates of change, of rates of change, of rates of change. In this lesson, we'll consider such higher derivatives from the point of view of physical applications, considering examples covering race car driving to robotics to ocean waves.
You know, and I know what happens when you differentiate a polynomial and when you keep differentiating a polynomial. Higher and higher derivatives give you deeper information, but polynomials are finite, and that means that eventually derivatives will annihilate a polynomial and send it to zero. Higher derivatives come with a number of different notational conventions. You may be tempted to write f prime, f double prime, f triple prime, etc. This is not so good in general. It might make your homework a little bit confusing to read. A bit better notation would be that which we used for Taylor series, denoting the nth derivative of f using a superscript n in parentheses. Better still is the notation df dx, d squared f dx squared, d cubed f dx cubed, etc. But this leads to the question, why is that notation used? Why is the second derivative not df squared, dx squared? Of course, the reason is that we're taking powers of the differentiation operator, d by dx. Where are these higher derivatives to be found? How do we interpret them? One good example comes from dynamics. If x, as a function of time t, denotes the position of a moving body, then one interpretation for the first derivative is as velocity, as I'm sure you've seen before in your introductory physics. You may also know that the second derivative of position is, indeed, acceleration. It is the rate of change of velocity. What about the third derivative of position? What is that? What about the fourth derivative? And higher still, do these have physical meanings? Well, they certainly do. The third derivative is sometimes called jerk. The fourth derivative, depending on which side of the ocean you're on, is either called snap or jounce. Now, maybe you've heard of these before, maybe you haven't. When might you need to know something about this? Well, if you're working with any sort of interesting system involving dynamics, a good example would be the quadrotor robots that can fly extremely precisely. From what does that precision come? It comes from careful control, not only of velocity and acceleration, but of jerk and snap as well. There are other interpretations for higher derivatives as well. One interesting interpretation comes from geometry and curvature. What is curvature? Well, you can certainly feel curvature when you're driving down the road and you make a sharp turn. You can tell the difference between a looser and a tighter sort of turn. The higher the curvature, the more you feel when you turn. But what is curvature really? Well, it seems from this physical explanation to have something to do with radius. If we had a circle that was tangent to our road, the point at which we're turning, then the radius r of that circle would seem to correlate somehow to the curvature that you feel as you go around. The smaller the radius, the higher the curvature. And indeed, at a point on a curve, one definition for curvature is as the reciprocal of the radius of the osculating circle, the circle that agrees with that curve to second order. We're going to do a somewhat lengthy derivation to get a formula for curvature. Consider a function, y equals f of x, and let's fit to it a circle that agrees up to second order. We'll say that the radius of that circle is some unknown, r, and we'll set up a coordinate system, x, based at the center of that circle. Now, at some value of x, the graph of this circle, that is square root of r squared minus x squared, is going to agree with f and its derivatives, at least the first two. Now, let's do a little bit of work. If we differentiate this equation, what do we get? We get f prime is equal to what? Well, we have to take the derivative of r squared minus x squared to the 1/2. That's 1/2 r squared minus x squared to the negative 1/2 times the derivative of what's on the inside, negative 2x. There's a little bit of simplification that goes on, and we get negative x times quantity r squared minus x squared to the negative 1/2. Now, this has to agree to second order, so let's compute another derivative. On the left, we get f double prime. On the right, what do we get? Well, we're going to have to use a product rule. First of all, we have minus quantity r squared minus x squared to the negative 1/2. Then we have plus negative x times the derivative of r squared minus x squared to the negative 1/2, which gives us a negative 1/2, then an r squared minus x squared to the negative 3/2, and then a negative 2x factor. There's a little bit of simplification we can do here by factoring out a negative r squared minus x squared to the negative 3/2. What we're left with is an r squared, a minus x squared, and a plus x squared. The negative x squared and the plus squareds cancel, and we're left with a r squared that we put out in front. So f double prime is negative r squared times quantity r squared minus x squared to the negative 3/2. Now let's step back for a second. At the point of tangency, we know f prime and f double prime. What we don't know are the values of x and, most importantly, r. That's two equations, two unknowns. We ought to be able to solve for r and get the curvature. Let's do some manipulations. Taking the first equation and squaring it gives us, on the left, f prime squared. On the right, negative x squared, that is, positive x squared, times r squared minus x squared to the negative 1. Now, if we rearrange that a little bit and then multiply through the f prime squared by the quantities on the left, we get f prime squared times r squared minus f prime squared times x squared equals x squared. If we rearrange again, factor out the x squared term, then solving for x squared gives us x squared equals f prime squared times r squared all over 1 plus f prime squared. Now, we can substitute that into the second equation, the equation for f double prime, and so eliminate the x variable. When we do that substitution, what are we going to get? We'll get that f double prime equals negative r squared times r squared minus f prime squared times r squared over 1 plus f prime squared, all of that to the negative 3/2. Well, we can factor out an r squared from that term on the right, do a little bit of algebraic simplification, and then some canceling of the r squareds, and we'll get that f double prime equals negative 1 over r times quantity 1 over 1 plus f prime squared, all to the negative 3/2. once we get that, then it's not going to be hard to solve for r. We'll get rid of that pesky negative sign by taking an absolute value, and then solving for 1 over r gives the curvature kappa to be the absolute value of f double prime over quantity 1 plus f prime squared to the 3/2. That's a complicated derivation and a complicated looking formula, but it's a very general formula for computing curvature. Now, how might we use this? Well, first of all, notice that curvature depends only on the first derivative and the second derivative. That makes sense since it's being captured by something to do with a circle and second order tangency. If we were in a setting, let's say looking at ocean waves, where the derivatives were fairly small, then we could approximate the curvature by saying it's f double prime times what? Well, if f prime is small, we can use the binomial series to expand it as 1 minus 3/2 f prime squared plus some higher order terms in f prime. You could work out what those are. There are a few other things that we see from this formula, namely that the curvature is exactly equal to the second derivative at the maxima or the minima of a curve where f prime equals 0. That's probably something that you want to remember. Curvature is really just the second derivative when you're talking about a max or a min. There are some other things that come out of this formula, namely that the curvature is 0 at an inflection point. And, as you might have already guessed, the sign of this second derivative determines the concavity of the graph, whether it's concave up or concave down. Yet another physical interpretation of higher derivatives comes in the subject of elasticity. Consider a deformable beam with a uniform cross-section and some static load, a weight that is applied that may vary with position x along the beam. What one often wants to know is how much does the beam deflect? This deflection, u, as a function of position, x, satisfies the following equation. The fourth derivative of the deflection is proportional to the load. Now, there are some constants of proportionality involved. One of them, E, is an elasticity based on the material the beam is made from. The other constant, I, is a moment of inertia related to the cross-section. You don't have to know what any of that is. We'll talk a little bit about moments of inertia later in the course. For now, the thing to know is that it's the fourth derivative of the deflection that matters in this elasticity problem. But of course, our final interpretation for higher derivatives is in terms of Taylor series, that they provide the means to get better and better approximations to functions.
Derivatives and iterated derivatives really are everywhere and all about. But what are they good for? In our next lesson, we'll consider one of the great applications of higher derivatives to optimization problems.